As I was saying before, if we're not going to go over every problem from the practice midterm on this exam review, because all those solutions were handed out, and then I did the walkthrough solutions and posted that on YouTube. If you do have a specific question, you can ask the question about the problem and we can go over it, but I'm not going to solve every problem during this. If you haven't watched those videos and you have a question about the practice exam, go watch the videos and then post your question to the ed board and I'll get to you on that. There was a question posted on the ed board about the amount of work that needs to be shown on the exam. Doctor, I've been TAing this class for about a year now, over a year, and I've never had anybody complain that they had points removed because they didn't show enough work on the midterm or the final. But Dr. Wayne grades those, and it's always, you know, better safe than sorry. So if you're worried about time constraints while you're doing the midterm, you know, it'd be safer to kind of go through all the ones that you can get done quicker and then go back. But if you had something, if it asked you to test for causality, and let's say you had something like h of n is equal to u of minus n, right?
You got to share again.
Oh, am I not sharing? Sorry.
You're good.
Thank you. So let's say this was on the midterm and it asks, you know, is this a causal system? Well, if you write in, well, h of n equal to -1, where typically you just write it like this, that's going to be u of -1. That doesn't equal 0, correct? So we could just write that equals 1. Our system right here, we have to look into the future to get a value. So that's not causal. So something, if you just do something like that, then that's perfectly fine. That she'll accept that as an answer. Or if it asks about memory and you say, well, you know, I need to integrate from -infinity to time t, and we could just say you know, some f of t dt. H of t is this. Well, this is going to require memory, because when I do this integral, I need to look into the past down to -infinity to get to this specific time to get a system output or to get a system response at that specific time t. Does that make sense of what I just said?
Yeah, it sounds like she's not looking for proofs. She's just more looking for reasons of the answer.
Exactly. Yeah. This isn't a math class, so you do not need to prove to have a mathematically solid, you know, proof to get the answer correct. If you do something that conveys your understanding of the problem, then and the material, then she's going to give you the benefit of the doubt. So I hope that answers that question. Now I'm going to kind of run through a couple of things that they don't spend a lot of time on in this class, mainly complex numbers, and then probably one or two other things about convolution, and then I'll open it up for questions. But one of the big things that people seem to have a problem with this in this class, because I feel like it just kind of gets thrown at you, is the whole complex numbers and complex exponentials. So a typical way to write a complex number is we refer to it as a complex number S, and it has an imaginary part, which is sigma, plus an omega. It has a real part, which is sigma, and an imaginary part, which is omega. So if I wanted to refer to the real part of S, then I would say that is sigma. And if I wanted to refer to the imaginary part of S, I would say that is just omega. Now, every complex number, we could plot it, right? Because if we had just a purely real number, like a normal integer, right, we could put it on a number line. 0. So say we had the number 3. Well, we could draw that on a number line just like this, and it's going to come out to here. Now with complex numbers, we have two different parts. So we can have what's called the S plane, and it has a real axis and an imaginary axis. Here's your real axis, here's your imaginary axis. This is the S-plane. And just for the sake of the exercise, we can say that S is equal to, we'll do 3 plus J4. And I come out 3 going this way. Now I'm at the real part of 3, or on the real axis I'm at 3. And 1, 2, 3, 4. Here's J4, right? So I put a mark there, and then here's my complex number. And you can kind of treat it like a vector or phasor. But if we wanted to talk about some of the properties of this phasor, well, we could say, well, it has a magnitude, right? That magnitude is the length of the phasor. So the magnitude of S, and just applying the Pythagorean's theorem, we get that S is equal to the square root of 3 squared plus 4 squared, or 25, or a scalar of 25 in this case, or 5. So the magnitude of any complex number S is going to be the real part squared plus the imaginary part squared. And recall that I said the imaginary part is just omega, right? Because if we put in, this does not equal the square root of the real part squared plus j omega squared, because this would be equal to sigma squared plus j squared plus omega squared, or excuse me, j squared times omega squared. And then that would be equal to sigma squared minus omega squared. And that's not equal to that, right? We're minusing it right here. These kind of all look the same. Sorry, this is the new app that I'm trying to get used to. So when we talk about the imaginary part, we are strictly talking about the coefficient of j, of the complex of the imaginary number j. Okay, that's a very important thing, because you can see right here, well, that messes up the magnitude. So when you want the magnitude, you take the real part and the imaginary part. Okay. And another property that we could look at about this complex number, this one right here, is it has an angle that it makes with the real axis, right? Now the length right here, this is j omega, the length of that, or it's just the length of that is omega, excuse me. And then right here, this is a length of sigma, correct? Which in our case are 3 or 4 and 3. So this is 4 and, or excuse me, I'm all messed up here. This whole time, that should be 3 plus 4j. I apologize. This would be 3 right here, and then this is a length 4, right? So if we wanted the angle of this, and that angle is right here, the tangent of theta is equal to the opposite over the adjacent. And in this case, that's going to be 4 over 3. And 4 is the imaginary part of S. And 3 is the real part of S. So the angle is given by the inverse tangent of the imaginary part divided by the real part, 4 over 3. And in this example, that should be, it's a 3, 4, 5 triangle, so that should be about 53 degrees. And if I wanted to put that in radians, then I would just multiply by pi radians divided by 180 degrees. And the easy way to remember that is that there is 2 pi radians per circle. There's 360 degrees per circle. So there's your what do we call that? Conversion factor. That, 360 degrees is equal to 2 pi. And then you can just divide by both sides by 2. And then whatever you need, you just divide it by there. So using what we know now about the magnitude and the angle, right? So S, magnitude S is equal to 5, and the angle of S is equal to 53 degrees. Well, we can write S a different way. That would be completely the same. It means the same thing. It's 5 times E the j 53 degrees. And looking at this, let's recall Euler's identity, that e to the j omega t, and I'm going to write it. You're probably familiar with it more along the lines of this: cosine of theta is plus j sine theta. But I could also write it just like this: e to the j times the quantity omega t plus theta. So I gotta let somebody in the room. And this way is much more meaningful to us because this is a radial frequency or an angular frequency, whatever, angular velocity. And then this is a phase shift. And as electrical engineers, we're gonna have to worry about frequencies and phase shifts. And if I write it like that, well, I take the coefficient of j and I plug it into my identity. I get omega t plus that phase shift plus j sine omega t plus that phase shift. And if I wanted to refer to the real part, if I said the real part of e to the j omega t plus theta, well, that would just be, so here's e to the j omega t plus theta. When I talk about the real part, well, that's just equal to cosine omega t plus theta. And a lot of times people get a little intimidated when they first get involved or introduce this kind of stuff about it being overly complicated. But after this week, after this midterm, when we get into the Fourier transform, you will see why we really like complex exponentials. Complex exponentials are eigenvalues or eigenfunctions to LTI systems, meaning that if we put a complex exponential into some LTI system and that complex exponential has a frequency of omega, then we're going to get out a complex exponential of frequency omega from that LTI system. All we're going to have is it's going to be scaled, right? So it could be amplified or attenuated, meaning we could have a positive gain or a negative gain. And then it'll have a phase shift, meaning that it's either be, leaded or lagged. But back to the example real quick. So I can write this like this. And if I wanted to expand this part here, 5 times e to the j times 53 degrees, I'm going to have 5 times cosine of 53 degrees plus j sine 53 degrees, right? And scroll down just a tad. Keep working through it. We'll have 5. Well, the cosine of 53 degrees, I'll plug that into my calculator here. That's about,
I got 3. Oh, no, sorry. You didn't put the.
it's gonna be roughly 1.8 ish. And this was an approximation, just to let you guys know that it's about 53 degrees. And then plus j, and then you do that sine.
How did you get 1.8? Because I did cosine of 53 and I got 0.60. Did you change it to?
No, I got 0.62. I don't know why I wrote 1.8 to be honest. I just multiplied it by 3 in my head for some reason. Oh, I know why I multiplied it by 3 in my head, but it should be, 0.6 roughly. And then the sine of 53 degrees is about 0.8, right? And when we distribute that 5 in there, 5 times 0.6 is 3, and then 5 times 0.8 is 4. So we come right back to our complex number written out. So this is called rectangular coordinates, and then this is called polar coordinates, or sometimes called, actually that wouldn't be a phasor, that is polar coordinates. An explanation on phasors, on a phasor coordinate. So a lot of times if you take a class on power systems, where pretty much everything we work with is in North America is going to be 60 hertz. In Europe, it's 50 hertz. But if I'm talking about the North American power grid, and I'm just talking about a bunch of buses and generators and transmission lines, everything is going to be 60 hertz. So I really don't even need to include the whole omega t, right? If I had some amplitude, let's say 120 volts, and it was it'd be 120 pi t, and let's put a phase shift in there. Well, this is my radial frequency, and omega is equal to 2 pi f. If f is 60, then omega is going to be 120 pi, right? So sometimes you'll see it written like this, 120 and an angle delta, where what we've dropped is the radial frequency. And if everything is the same frequency, then this is fine. We can continue, we can do our phasor math this way, and nothing's gonna be affected. But if we have different frequencies, then we cannot do our math in this form. We need to keep it in this polar form or the rectangular form. Just but that doesn't even really apply to this class, so I don't know why I said that. Apologize. And does everybody understand? Does everybody understand how I went from when I'm talking about the magnitude, how I can go from the magnitude, and I have the coefficient of my complex exponential, and then how I got the angle and how I go back and forth?
Yep.
Okay.
Yep.
And now we're going to discuss one more thing when it comes to the angle. So the range of tangent of theta is going to be that's going to be, you know, negative 90 degrees or negative pi over 2 to 90 degrees or positive pi over 2, correct? And what if I had, let's get rid of some of this. If I had a complex number that was out here. If it's out here, then my my sigma is obviously going to be negative, right? So let's just call it negative alpha. And then my imaginary part is going to be, we say, positive j beta. And I want this angle. And that angle is theta. Well, if I do the tangent of the inverse tangent of the imaginary part divided by the real part, I'll have negative alpha in the denominator, and I'll have beta up top. And this is equal to negative beta divided by alpha. And there's a trig identity in here, and that trig identity is that negative tangent. Then the negative, I'll just write it out because I don't even know how to say that. So the inverse tangent of a negative angle is equal to the negative inverse tangent of that same ratio, not angle. So, and if I do this, what's going to happen is that this beta and this alpha would be out here somewhere, right? So here's my angle that this would give me. It would give me this angle, and then when I negate that, well, then that's just coming down to right here. So if we have a negative real part, then it's not going to work. So if my complex number is in the first or fourth quadrants, this is Q1, and then Q2, Q3, and this is Q4. So if my complex number is in their first or fourth quadrant, then it's just the inverse tangent of the imaginary part divided by the real part. And that gives me the correct angle. And if it's not, then what I need to do, if we look at this and we take another look at this angle here, and we call this one phi. This angle phi is given by, we have our opposite side over here, right? Which is beta. And we have our adjacent side here, which is just alpha, not negative alpha, just alpha. Phi is equal to the inverse tangent of beta divided by alpha. That means that theta is going to equal 180 degrees minus phi, or 180 degrees minus the inverse tangent of beta over alpha. Does that make
Can you
sense
go
to
back
everybody?
Yes. Can you go back over about the inverse of the imaginary divided by the real part when that comes into play again?
It's always, whenever you're talking about getting an angle, it's always going to be, when you take the inverse tangent to get that angle, it's the imaginary part is always on top. And that's from when we look. So here's our angle on this one when we're down here, right? Well, tangent of theta is equal to the opposite over the adjacent. Yeah.
Totally.
Well, my opposite side is the magnitude of my imaginary part. My adjacent side is the magnitude of my real part. And it doesn't matter what quadrant it is in, as long as we pay attention to knowing that, you know, we might have to be subtracting it from 180. And we can do one more thing just to show that it works everywhere, is that if I come out here, well, now my angle is theta, and my angle right here, this is phi, and I am now at, let's call this negative j beta. If I plug in that negative there and that negative there, then what this becomes is theta is equal to 180 degrees plus the inverse tangent of beta over alpha. And you can see that that's going to give me the angle that I want. This right here would be phi now, this term. So if you have a negative real part, then you do 180 degrees minus the inverse tangent of the actual value of your imaginary part, meaning if you have a negative beta or a negative imaginary part or a positive imaginary part, you plug in that sign, right? But it's the real part that determines, do we need to subtract this from 180? And the best way to do this is anytime you are given a complex number, and I'm kind of foreshadowing a little bit here, and it's kind of because this class is very abstract in the beginning, people don't know why they're taking it. But imagine I had some transfer function, h of s, and that is equal to 1 over, we could say s plus 1, right? And I wanted to know something about my steady state system response. If I'm talking about steady state, then I change my s to just the imaginary part. And if you guys want to know why that is, I can tell you, but right now let's not worry about that. And this becomes 1 over j omega plus 1. And I want to know the angle of this right here. Well, if I want to know the angle of this, I have my s plane, I'm at 1 right here, and then if whatever j omega is, if I plugged in some value for omega, then I would come out and I would have a number like this. And here's my angle. Now, if I had 1 over, but when we get to the point that I was trying to say, is I would just draw a little triangle. I go positive this way, and I go positive this way because omega is going to be positive, right? Then my angle is somewhere in there. Now, if I had 1 over, or we can just say if I had negative j omega minus 1, I can draw a triangle. Well, my real part right here is going this way. My imaginary part right here is going that way. And I'm always taking my angle with reference to the real axis. So now I can kind of see, all right, I have to subtract 180 or add 180 or do whatever you need to do. So if you need to draw a little triangle, you know, sometimes I do it still. I don't ever just look at it and sense it, just because when you're trying to do these calculations, there's a lot going through your head. So draw a little triangle if you need to. Here's my real part. Here's my imaginary part. Here's my angle of reference. I come down, and now how do I get my angle? So trying to think if there's anything else about complex numbers that we need to talk about. I don't believe so. Does anybody have any questions about complex numbers? I mean, I don't think it's going to be absolutely imperative that you're an expert with complex numbers to do well on this midterm exam, but pretty much every class you take from now on in electrical engineering has a bunch of complex numbers. You have to be comfortable going from a rectangular coordinate to a polar coordinate, which, remember that this is a polar coordinate, and you have to be comfortable using phasors, and a phasor is something like 120 with some angle delta. So that's a phasor notation, and this is a polar notation, and then we had the rectangular, and this is a rectangular coordinate right there. Is everybody comfortable with it, with at least these two here?
Yes.
Okay.
Yes.
If you're not, please say so. We can go over it even more. If not right now, at some other time. Okay. Next, I'm going to talk about two things that seem simple but are very important. That's the unit step and the unit impulse. So in continuous time, the unit step is defined as 0 for t less than 0 and 1 as for t greater than 0. And the reason that we have no equal to here, less than or equal to, is you can think about the unit step as it's coming along here, it's motoring along, and it's kind of turning on. It has a rise time associated, and real applications, when we're actually trying to engineer something, we have to take into account this rise time. So even if we apply, the voltage, even if we apply the voltage right at, what we think is t equals 0, it's never going to be perfect. But we don't really have to worry about this rise time. I shouldn't say this rise time. We don't have to worry about what it's equal to at 0 in most applications, and certainly not in this course. So if that hangs you up, try not to get hung up on it, because it doesn't really matter. And if we wanted a time delayed version, that's 0 for t less than t naught and 1 for t greater than t naught. And a good way to think about the unit step is all it does is it turns something on or it turns something off. If I had some signal y of t is equal to x of t, where x of t is a non-zero values from negative infinity to positive infinity. Well, my y of t is only going to be non-zero in between 0 and 2, because at t equals 0, this one turns on. At t equals 2, that one turns on. So y of 3 is going to be equal to x of 3, u of 3 minus u of 1. X of 3, I don't know why I started writing a 5, but I get 1 minus 1, which is equal to 0. So we use these pretty much as switches. And as engineers, it's going to be helpful to think about things coming on and things coming off. But when you do have something that's defined by a unit step, we can rewrite the function so it appears a little more, mathematically intuitive. And we could always rewrite it as a piecewise function. So y of t is going to equal x of t when t is in between 0 and 2, and it's going to be 0 otherwise. That's sometimes people get hung up by the unit step, but it's really nothing more than that. We can scale it. You know, we could multiply it by you know, we could and each one of these we could write a 2 there. So then this would just be 2x of t. But we can scale it and we can time shift it, and that's all we use it for, is to just kind of turn things on and off. Does anybody have any questions about the unit step?
Nope.
Okay.
Good.
I don't have my little chat window up too, so if any of y'all see a question in the chat, let me know, please. But, and now we have the delta function, delta of t, and that is equal to 1 at t equals 0. Yeah, somebody's coming in. That is equal to 1 at t equals 0, and it is equal to 0 otherwise. And so if I had y of t, and once again, we'll assume, we assume x of t is non-zero on negative infinity to infinity. Y of t is equal to x of t times delta of t. Then y of t is going to equal, oh, let me write it like this. We could rewrite y of t as a piecewise function like this. Y of t is going to equal x of 0 and 0 otherwise. So the delta function, right, it is only non-zero at t equals 0. So if I put in y of 1, I would get x of 1 times delta of 1, which is equal to 0. And if I put in y of 0, I would get x of 0 times delta of 0, which is equal to x of 0. Any other value I put in is just going to, for t, is going to cause the delta function to become 0, which makes my output 0. And it has the same property with as far as the time shift. And we can actually write that out just for the sake of it. So delta of t minus t naught, and that's equal to 1 when t is equal to t naught and 0 otherwise. So if y of t is equal to x of t times delta of t minus t naught, well, if I put in y of t equals 0, I get x of 0 times delta of 0 minus t naught. And as long as t naught is equal to 0, that's right, t naught not equal to 0, then this becomes 0. But if I put in y of t naught, then I get x of t naught times delta of t naught minus t naught, which is equal to x of t naught times delta of 0, which is equal to x of t naught. And that's the sifting property, isn't it? That was covered in, I can't remember if it was week 1 or week 2, but that is the sifting property, which is an important. Let me make sure that I'm calling that one correct, because it's been a while since I looked at the book. Excuse me, that's the sampling property. The sifting property has to do with convolution. So this is a sampling property. Let me write it out discreetly. Let's do it in a different color, because this is This is a fundamentally important one. X of t times delta of t is equal to x sub 0 times delta of t. Which you could just write like this. I mean, it's kind of the same thing because we know that this is only going to be on at the 0. I mean, but if you wanted to write it like that, then this is like writing like a piecewise. I'd have to put my bounds in there. This delta of t just kind of gives us a shorthand to not have to write the piecewise. And then the other one is that x of t times delta of t minus t naught is going to be equal to x of t naught times delta of t minus t naught. So this is the sampling property. And this is important because what if I had a line of delta, if I had what's called an infinite impulse train. So I just have impulses going up and down the t-axis, and then I have some signal. I can sample this signal by convolving this signal with this infinite impulse train, right? Because if this is h of t and this is x of t, and I say my output is y of t, and that's equal to x of t convolved with h of t, and now we get to use some properties. We'll say x of t, and this is convolved with, and let's just I'm just going to do a couple impulses. I'll just do like, you know, this one, so that we don't have to write a whole bunch. But this one right here is going to be delta of t plus t naught. This one right here is delta of t, and then this one right here is delta of t minus t naught. So I could rewrite h as delta of t plus t naught. Right. And convolution is, it has a lot of the normal properties of arithmetic. It's commutative, it's distributive, it's associative. So this becomes x of t convolved with delta of t plus t naught plus x of t convolved with delta of just t plus x of t convolved with delta of t minus t naught. And now we're not talking about the sampling property. Now we're talking about the sifting property, right? Because I'm not multiplying a signal with a impulse. I am convolving a signal with an impulse, correct? And what the sifting property says, and if we think about this, if we try to think about this in an intuitive sense, I guess. Oh, that's way too big. Oh, damn computer lags. There it goes again. How do I move this? There, look at that. So if I'm convolving this one, we can say that this one is this is the impulse associated with t minus t naught, right? Or just it's the impulse associated with the impulse at the origin. And I go to pass this through the signal. It's going to come up here, so I'm going to flip it. It flips, it's symmetric. Now I'm passing it through the signal. And you can see that at this point in time, my convolution, so this is for one specific moment in time, right? I would have y of t is equal to, well, it's equal to the impulse, which is, it's equal to the area, excuse me, it's equal to the integral of the impulse and x of t. Well, that's just equal to x of t at that time. And I move it along just a little bit further. And now I every time I take a snapshot in time to get my output, it is just my impulse pretty much times my output signal, which just gives me my output signal. I say it's just my impulse, but technically you have to integrate the impulse because that's the integral of that is the area of 1. But I think this kind of gets across the point that we can use an impulse to sample. We keep passing it through, and this is just every time I stop it, it's just a different snapshot in time. So here's y of one, y of a certain value of t, y of another value of t, y of another value of t. And this is the sifting property. And what the sifting property says is that x, that doesn't stand out one bit. X of t convolve with delta of t is equal to x of t. This is very important. And it's important that you understand this and why that is. And the other part of the sifting property is, and the sifting property, or the sampling property that I wrote is the same in discrete time as it is in continuous time, and same for this one. If we could talk about, we could replace t's with n's and we don't lose anything. So don't worry about that. But and then x of t convolve with delta of t minus t naught is equal to x of t minus t naught. And this is important. What this is saying is that if we convolve our signal x of t, okay, we take our signal x of t and we convolve it with a delta function, that time shifted delta function, then we get out that exact same signal. However, it is just now replicated along, it is replicated with the center of it at that time shift. And let me try to explain that a little bit better. Here's x. Here's h1, and h1 is an impulse at the origin. Here's y1. If I convolved x with h, if I convolve x with h, here's what I'm getting. Same exact signal, centered on that impulse. Now, if I had an impulse here, there's let's say this is 1. So h2 is equal to delta of t minus 1. Here's my y. Here's 1. Y sub 2. Where's my center? That's my center right there, just about. Here's my output. And I'm going to rewrite that because this is one of the fundamental ideas of this course, that, you know, you're not going to have to do very many convolution integrals ever again after this course. It pops up here and there, like saying like, hey, you know, this idea is convolution. You learned it in signal systems, but you're not going to actually have to perform any convolutions probably after this course. If you take a digital signal processing course or a 304, you're going to have to understand, you might have to do a couple quick DT convolutions to kind of get an idea about something, but it's very important that no matter what class you really go into after this, in this, at least this degree plan, you have to understand what convolution is and some basic properties about it. And if you understand those properties about it, you never have to do the convolution because there's ways to work around it. But delta of t is equal to x of t. And we can see that in this one right here, right? Because this y of t was x of t convolved with delta of t, and x of t involved with delta of t minus t naught is equal to x of t minus t naught. And that's this example right here. How's everybody feel about that? Is that kind of being understood by people? I know it still might be a little foreign of a concept, but when you see this, just think it's replicating my signal. And if you see this, well, it's replicating my signal, but it's shifting it. And remember, we can break apart any infinite impulse train into, so h of t is that infinite impulse train. We can break that apart into just a bunch of delta functions. And when we have just a bunch of delta functions, well, now look at, we can spread this convolution in there and spread that convolution in there. So now I have my signal replicated at minus t naught. I have my signal replicated at the origin, and I have my signal replicated at plus t naught. And because y of t is the sum, so if I had, let's say that this is x of t and it goes, let me try to get this a little bit neater. Let's say it goes from, we'll go. And if we say this is 1, -1, and then -1, x of t minus, let's say 0.5, or let's do plus 0.5. Actually, I want to do plus 1.5. So if I shift it 1.5, that means I'm going to be right about here. Hold on. Sorry, I get my scaling all messed up. I should do like this. And let's say y of t. So this kind of results from this formula right here that we just broke apart. Let me kind of clean up some of this. Right, so that would just be that this t naught would be this t naught would be 1.5. What am I doing with my scaling here? I'm kind of messed up. I shifted that. That's just 0.5. 0.5, and then this is just 0.5. Sorry. I should just use one block as one unit instead of always doing this myself, but I'll never learn. So these three signals, right, kind of look like this. This is all I'm doing is kind of drawing this example up. Now y of t is the sum of these three signals, right? And I'm going to clear out some of this. So y of t, and we get, and all those signals, this has amplitude 1, amplitude 1, amplitude 1. And then this would be right here. This is 1.5 and 0.5. And this is negative 0.5 and 1.5. And if I wanted to draw this out, what my y would look like, well, at negative 1.5, I come up and I'm here. And I come to right here. I'm gonna need more room. And now I gotta add it. So this is negative 1.5 over here. That was a 0. And then I was 0 at this negative 1.5. But now when I get to 1, I have another value here. So now I need to add it. And I keep coming along and I get to this 0.5 and the negative 1.5, negative 0.5, 0, 0.5, and 1.5. And now when I get to this negative 0.5, now I have to add this signal into it. So I come up and I come up a little bit more. And I go along. And I can see that right here. Well, this one turns off now. So now I would come off. And I would go forward. And at 1, this one turns off. So I come down here. And then at 1.5, this one turns off. And bam. So I was able to predict what my signal is without having any mathematical definition of my signal, I can draw out what my signal is going to be when I sample it with some delta functions just by using these properties, the sifting property. And then this is a result of the distributive property. And this is really nice when we're talking about any kind of DT convolution, because if you know how to use these properties, and they're all pretty simple because these ones are not difficult to remember. I mean, if you can pass a calculus 3 test or a linear algebra test where you have, crazy differentials and everything like that, then you should be able to remember these two simple properties. Now, if I have any kind of DT signal, well, I can make any DT signal look like a sum of impulses, right? If I had a sine wave in DT, then each one of those impulses is going to have a scaling factor and a time shift. And I can do any kind of convolution I want because I can take that sine wave, I can make it impulses, and then I get a very easy output because it's just going to be the sum of a bunch of scaled and shifted inputs. Does that make sense?
Yep.
Okay.
Yes.
So I so I went over the delta function, went over the unit step. I kind of rolled into the convolution. How's everybody feeling about this? Was kind of like a mixed convolution because the impulse train was kind of CT, but it's kind of like this is almost like a DT convolution. How does everybody feel about DT convolutions, or is it mostly CT that's hanging everybody up?
Mainly CT for me.
Okay.
Yeah, it was the CT, but we went over the limits the other day and it cleared up a lot for me.
Okay. I'll try to do that same thing right now. And then after this, probably open up for a couple questions.
Where are those videos that goes over the midterm questions? You had videos on it?
Yeah, I posted the links on the ed board like 2 or 3 times already.
Oh, I'll look at it again. Sorry.
That's all right. I just
Will there be much on the Fourier stuff?
Yes.
if you can, I'll tell you right now, if you can do the practice midterm, no problem. You will not have any problem on the exam. The Fourier series, the formulas look complicated, but all a Fourier series is a way to write cosines and sines, essentially. I mean, we say it's any periodic signal, but we're talking about cosines and sines, is what it boils down to. And if we go back to what we were talking about earlier with the complex exponentials, either j theta is equal to cosine of theta plus j sine theta. How can I get a cosine out of this? Well, if I wanted to just write cosine of theta, how do I get that? Well, I said you could take, just the real part of this, but if let me do this. If I do e to the j theta plus e to the negative j theta, and I'm going to write a couple trig identities over here. Cosine of theta, cosine of negative theta is equal to cosine of theta, the even function. Sine of negative theta is equal to negative sine theta. That's an odd function. All right, these are a couple of trig identities that you should know. You should always know this, that if you see a sine of negative theta, that is negative sine theta. But if I write this out, then I'll have cosine of, I'm going to drop my parentheses, cosine of theta plus j sine theta plus cosine of theta. And now I have a plus j sine of negative theta, correct? Look at this identity right here, this bottom identity. So that means that this is the same thing, minus. That's from that identity, right? So now I look at that. Well, I have a plus j sine theta and a minus j sine theta. So that goes away. And I get e to the j theta plus e to the negative j theta. is equal to 2 cosine of theta. Or cosine of theta is equal to 1 over 2 e to the j theta plus e to the negative j theta. And now my Fourier coefficients, a of -1 equals a of 1 is equal to 1/2. There's the Fourier coefficients for a cosine. I
So
can
does
get it
that
right.
have to do with why you can break down any signal into a even and an odd form?
Well, when it comes to the even and the odd stuff, it gets a little different because when you're talking about complex numbers, if it's an odd function, so let's real quick, let's look at let's do a sine and we'll see something here. So if we wanted to, instead of going through this whole derivation, I'll just write this real quick. E to the j theta minus e to the negative j theta. I'll just do it all. It's good. It doesn't hurt. I get cosine of theta plus j sine theta minus cosine of negative theta, but cosine of negative theta is equal to theta. So I can just write theta, and then I'll have a, well, this would be in parentheses, plus j sine negative theta, right? And if we rewrite that, we get cosine of theta plus j sine of theta minus cosine of theta. Now, this quantity right here is actually equal to negative j or negative j sine theta, right? So when I distribute this negative sign in there, I get a negative times a negative on the sign. So I get positive j sine theta. Does everybody understand how I went from this to this?
Yep.
Okay. And now looking at this, we can see that cosine and this cosine are going to cancel out. So I get e to the j theta minus e to the negative j theta. And if I divide that by 2j, then I get sine theta. And let me write this like this, do a little cleaner. I get 2j sine theta. And that means that sine of theta is equal to 1 over 2j e to the j theta, and then distribute minus 1 over 2j e to the negative j theta. And now sine is an odd signal, right? So a of -1 is equal to, here's this one would be -1. A of -1, the coefficient is 1 over 2j, and a1 is equal to 1 over 2j. But what we have here is these are conjugates of each other. If I go back to my complex plane here, if I write, well, let's take a look at this identity real quick. Anytime I didn't talk about this earlier, but let's say I had this number here. Let's just say it's a 1. All right, so this is s equal to, or 1 is equal to s sub 1. If I'd say s sub 2 is equal to j times s sub 1, well, that's j times 1, or just j. Here's s sub 2. And now s sub 3 is equal to j times s sub 2. That's equal to j squared, which is equal to -1. Here's s3. And just to finish it, we have j times s sub 3. Well, that's equal to -1 times j. That's equal to negative j. Here's s sub 4. So anytime I multiply a number or a complex number by j, I have 90 degrees of rotation. That's a handy way, or I shouldn't say handy way. That's helpful to know that, to be able to see that, to visualize that on a complex plane. That kind of makes things sometimes a little bit easier, because j is a funky number, and it's kind of this course is where people start getting involved with using J's a lot. So I like to try to point that little way to think about that out. And if I divide by J, well, dividing by J, I would just be rotating negative 90 degrees, correct? And 1, if I have the number 1, right, and then I divide this number by J, well, then I've just rotated 90 degrees this way, correct? So that's equal to negative J. So here's an identity. But so we could rewrite each one of these as this would be J over 2, and A1 would be equal to negative J over 2. But what we have are complex, these are conjugates of each other. So any complex number, it has a conjugate. And a conjugate just means it has the same real part and the opposite imaginary part. But these are conjugates because if we looked on an S plane, well, here's A of -1. We could say that this is J over 2 or 0.5J, and then right here this is negative J over 2. So here's one, and then here's one. Complex conjugates. If I had, and just to show, in case some people are so confused about complex conjugates, let's say I had a number out here. We could say this is 3 plus 3J. Well, there's a complex conjugate right here. This is 3 minus 3J. That's what a conjugate is. I just had something in my head and I can't remember what it was. But anyway, I mean, if you when it comes to the Fourier series coefficients, it's literally you're pretty much taking Euler's identity a lot of times and expanding it and then getting these. If I had a sine squared, right, that's equal to and that's E to J theta minus E to negative J theta over 2J, and then that's all squared. Now I just carry this out. I mean, I can't multiply this right in because this is a sum, but I could easily rewrite it, you know, E to J theta minus E to the negative J theta. First times the first, so we get E to the J 2 theta. We have that one. That's plus, or I guess it'd be minus sign, so it'd be minus E to the J theta times E to the negative J theta, also known as 1, because this becomes E to the J 0, right? Because if I have E to the A times E to the B, that's equal to E A plus B. So I have E to the J theta times E to the negative J theta, which let's circle this, I'll erase it, but that becomes E to the J theta minus J theta, which becomes E to the 0, which is equal to 1. Did everybody get that?
Yeah.
Okay.
Yep.
So I'm gonna erase all this and write 1. And now we do the second part. This is the same exact thing we just did there. We'll end up with a number 1. So we could just write 2. And then we have E to the negative J theta times E to the negative J theta. We have minus minus, so that becomes a plus. We get plus E to the J 2 theta. And we can do a little rearranging. So we have E to the J 2 theta plus E to the negative J 2 theta. And that's minus 2, right? And remember that we had this term here, so we have to square that. So that would be 2 squared times J squared. So that would be -4, right?
Where did that negative?
J squared
the-
is
in the numerator?
this one right here.
No, the negative J 2 theta, the middle term.
Oh,
Wouldn't
I
that,
just, oh, sorry, this was supposed to have a negative sign right there. This last term right here. This last
Okay.
term right here was a result of this multiplication, and I just forgot to put that negative sign there. Apologize.
okay,
Does that answer your question?
yes,
Um, and now we have this. So let's look at this. Let's piece this apart. So let's give myself a little room here. A to the J 2 theta plus E to the J minus J 2 theta and minus 2, and that's all over minus 4, which is equal to, let's factor out in the front there, we will do -1/2. Actually, we'll factor out a negative, yeah, we'll just factor the -1/2 on the front there. So then we have E to the J 2 theta plus E to the J 2 theta, excuse me, there's a minus sign there. And then that's divided by 2. And then this would be plus 1/2, right? Believe I did that correctly. It's just arithmetic, so it probably might have to be careful. But then this becomes 1/2 minus cosine 2 theta over 2. Or, in the familiar trig identity you probably know, 1 minus cosine 2 theta. And there's a proof of a trig identity using Euler's formulas just by playing around with it. You know what I mean? That's why complex exponentials, I mean, they're once you get used to them being in your life, they're awesome to have in your life. You never want to go away because they make things simple. But I don't remember what I was talking about. So if anybody has a question on how we got to that, I just kind of started writing stuff. I apologize. Did that make sense to everybody though? Do they understand like how to do the complex arithmetic? It just works the same way. You just get some J's in there now that just make signs flip and whatnot. Any questions about that?
No, I'm going through the third week homework now, and it seems like the lectures really went into a deep dive on theory. I don't know, but I'm doing the homework and I'm watching this, and it seems like it's just a lot of like converting between the two and like using identities to get it to appear how you want to.
Yeah, I mean that's kind of what it is. In the formula, you have AK is equal to 1/t, the integral from t, x of t, e, what is it? Negative j k omega naught t dt. This right here is like a normalization. That's all it is. We kind of, I ran out of room. That's what we're doing because we're integrating all of t. We have to normalize it, and we normalize it by dividing by the period. What does anybody have a question about what a Fourier series is trying to show you? Or when we talk about the spectrum of a signal, does anybody not know what that means? If I wanted to talk about, well, what's the spectrum of the signal look like?
Yeah, could you go over that?
Yeah, okay. So one of the things that we really care about is the frequency content. And as electrical engineers, and more so in other concentrations than the other, at least as students, we care about frequency content. And after this week, when we get into the Fourier transform, you'll this is kind of a little foreshadowing to it. But let's say I had a signal y of t, and it's equal to cosine of omega t plus cosine of 10 to the 3 omega naught t. So this is a periodic signal, right? I'm gonna have a very fast part and then a very slow part compared to each other, right? When I talk about the spectrum, if I were to take a look at this, and now I am on this is the frequency domain. So this axis here is omega, and this right here is the amplitude of big Y of j omega, which is the Fourier transform, which we're not there yet. So it's not important that you don't understand that. But when I'm talking about the spectrum, what I'm saying is, well, I have a bump right here at omega naught, and then I have one, and don't let this bother you too much, but at minus the omega naught, I get a bump there. And because these both have the same scaling factor, right? They're both coefficients are 1. So let me try to make these the same height then. And then if I were to come down here at, this is 10 to the 3 omega naught. And then if I come down here and imagine this is a straight line, I apologize. This is minus 10 to the 3 omega naught. What we're looking at is this is like the spectral content of our signal. Our signal is a superposition of two sinusoids, right? And one of them has a frequency of omega naught. The other one has a frequency of 1,000 times omega naught. And so if I look at the spectrum of it, I'm going to have bumps at those different frequencies. So minus 10 to the 3 omega naught. And like I said, don't worry about this minus sign too, because we could, and it's, I don't know if you do it in one of the labs in this class, we could put everything over to one side and then just, but it's not important because it's this is an even function, but this is the frequency content. I know I wrote the minuses there and said, don't let them confuse you, sorry, but you really don't have to worry about it, the idea of a negative frequency in this class, or probably even 304 if you take it. I don't think you have to worry about negative frequencies in that one. But when we talk about the spectrum, that's what we're talking about, saying, well, it's the frequency content of the signal, right? So if we were talking about a piano and we hit a key all the way down towards the right side of the piano, well, we'd have a high, our frequency content would be something that's higher on the omega axis out here. And if we hit one of those keys down on the low side of the piano that make that low sound, that signal would have some low frequency content. Low frequencies correspond to deeper sounds, and high frequencies or higher pitches and lower pitches. Does that answer your question, like very briefly? Because it's not totally important right now. I don't want to get too ahead.
Okay, so what is the Fourier series trying to show us then?
So if I wanted to do this as a Fourier series, if I wanted to write this as a Fourier,
like conceptually, like I tried to follow like the harmonics discussion from the video.
That's it, and that's what it's. When we write it as a Fourier series, I'll write this as a Fourier series real quick. We have 1/2 e to the j omega naught t plus 1/2 e to the j omega naught t plus 1/2 e to the j 10 to the 3rd omega naught t plus 1/2 e to the negative j 10 to the 3rd omega naught t. I don't know where the hell that just went. There's a t in there. Let's say that we were running some system, and we plan on putting things in. We plan on inputting controls at a frequency omega naught, right? That's the frequency of our input, of our control input, is omega naught. And let's say that we pass that signal into the system, right? And then just for shits, or excuse me, just for fun, we'll say that this is our system, right? And then this is our output. And I'm talking here's an X, we put it in, here's our H, and then we get this output. And for some reason, I have a harmonic in this system that when I put in an omega naught, it gives me there's a harmonic in there that will give me some output, some high frequency output, and it actually has almost the same amplitude as I want my my control output to be. I don't really have time to get in the conceptual of harmonics, but like all a harmonic means is it's kind of like it's a integer multiple of whatever this one is. So a harmonic is always going to have the same fundamental frequency. So 2 pi cosine of 2 pi t. The first harmonic of this would be cosine of I multiply it, that'd be 4 pi t. And then another harmonic would be cosine of 6 pi t. And then 8 pi t. And then 10 pi t. And then 12. So that a harmonic is an integer multiple of like a base frequency. That help.
Yeah. So how does
Um,
that relate to the Fourier transform then? Is it the Fourier transform is just like the
Well, because I get my fundamental frequency, right?
is it just like decomposing a signal into its different harmonics?
Exactly. That's exactly what it is.
Okay.
Yeah, that's exactly what it is. But yeah, so I had a little outline that I was going off of, but I'm not really good at even sticking to those. I'm kind of all over the place whenever I do this stuff. I apologize. I just like it and I think it's fun for some reason. But if y'all have any questions, you can feel free to ask and I can answer.
Really quick, just to go off of, I don't know if this is allowed or anything right now in this type of environment, but I think it could be very useful and fundamental if you can go through maybe like the first question of the homework.
I cannot, because I don't know if anybody has done them. I don't know if everybody's done them.
Or what about we just pick any
For which
Okay.
we're kind of as related to convolution, like a Fourier series.
no, the Fourier series, yes. Let's see. I'm gonna look at the textbook and if we can choose something that's not in part of the homework assignments.
I have, just so you know, I got about 15 more minutes too. I tell you what, if you wanna ask a question, or I mean, well, let me see. I'm looking at the textbook real quick now too.
I mean, looking at 3.3,
Okay.
couldn't you? I know for example, the fundamental frequency of that is pi over 3, right? Couldn't you just change it up, for example, make it just the fundamental frequency being pi, and then we can use this problem as an example?
Hey, Carlos, I'm working on the homework right now. So if you've only got 15 minutes left, if you want to, if you're on Discord, I can help you out with 3.3.
I'll appreciate it then.
What's
If the question is like, what am I struggling on that? It's I'm getting to the point because, on the textbook, it gives you the answers for the initial ones. Right. And I know I am breaking it down to the corresponding coefficients, but I know when I go to A of 5 and then A of -5 on this one, I'm getting two different answers from what it is the answer on the textbook. And it's giving me, I believe the answer in the textbook is -2 of J when it's going to A of 5. And I just need a little bit more help
What's,
to do that.
so we know the textbook answer. What answer are you get?
I think I know the question he's asking. It's that when you have the same coefficient for real numbers, it corresponds to the negative alpha value. So like a of 2 is like 7, then a of -2 would also be 7.
Yep.
If you have a complex number, then it's the conjugate of that. So a of 5 would be -2, and a of -5 or would be -2j, and a of -5 would be +2j. And I think that's asking is why is that? Does that make sense?
Yeah, that's just,
Is that the question, Carlos?
Yeah, it is. I mean, when you work it out, you get all the coefficients on this question. I'm looking at my homework really quick to so I'm not just speaking out of mind here. So yes, I got my a of 5 being 2 and my a of -5 being -2. And then when you look at the textbook answers, it's I guess you need to deal with something with the conjugate. And so
well, you're missing
specific,
you're missing a J on that A of 5. You dropped a J somewhere in your math.
well, I'm not trying to show my screen since this is the homework, right? But if Steven can help me out with this, then I'll just I guess I'll just ask for
And you-
this session.
Yeah, and just to let you guys know that if we're talking about homework assignments or work that needs to get turned in, like if it's the practice problems she puts out, you can post anything you want on the ed board with all your calculations. If it is a graded assignment, anytime you guys can send me send the staff a private ed post, and I'll look at your calculations. You know, the book has the answers. You can pretty much Google anything. So I'm not concerned about you getting, I care more that I'd rather have you ask and figure out where you're going wrong. So that way we can get you on the right path to get the correct answer, then Google an answer and just turn it in for the points. You know what I mean? So don't ever be afraid. Just if it's something that's getting graded, just send it private. And I'll always take a look at it. I'll try to, sometimes I'm not going to give you the answer because I don't think Dr. Wayne would like that. So I'll try to steer you towards it, but I'll do whatever I can and I'll respond as many times as necessary. I don't really have much else to say.
I mean, I think that would be helpful if you just want to go over real quick how when you're decomposing a Fourier series.
With
how
that,
you
with
get the
that
same-
formula,
What's that? No, how you get the same, you get two different values or one value of two different A's. Right? So a of 1 would be like 7, and then a of -1 would also be 7. But if they're complex, then they would have to be conjugate pairs. So the a of 1 would be J, and then a of -1 would be -J.
but that's what we just went through that. I mean, that's just,
Oh.
I don't really know. I don't know. I mean, I know a lot about this stuff. I'm not a mathematician when it comes to complex analysis. I don't have a reason off the top of my head
Okay.
why it's going to be like that. But here's an example of, well, we had a sinusoid, right? And we had a sinusoid that was an actual sinusoid and not a cosine. And when we take Euler's identity, we can see that, well, this is the coefficients we get. And this is 1 over 2j is the conjugate of -1 over 2j. That's why and I mean, sine is an odd signal, correct? Cosine's an even signal, and we saw with the cosine, we saw the cosine was just this. Cosine's even, and we have a1 is equal to a sub -1. And for the sinusoid, that's an odd signal. We have, this is right here, this is a1, and this is a of -1. and they're conjugates of each other.
So then you get opposite values, opposite signs for their values. Up
Yeah,
because you see that it's, yeah, negative J and then J.
Yeah, you get conjugates. So if I had I could write this in polar form. So 1/2J is equal to negative J/2, correct? And if I write that on an S-plane, here's my S-plane and sigma, then this is what my vector is going to look like, right? Is that magnitude of 1/2, correct?
Yep.
Then if I wanted to write this out in polar form, well, here's an angle, and this angle is equal to -90, right? And we said that when polar form, we care about magnitude, which is always positive, and angle. So 1/2J is equal to e to the j, e to the negative J times 90, or in this class, we typically use radians. Radians are actually better to use when you get introduced, because radians work out a lot nicer mathematically. And then this conjugate right here, 1/2J is, or -1/2J, that's equal to J/2. So that's coming up here, right? So this is going to be equal to e to the j pi/2. Now, when I talk about a conjugate, I just mean swapping that sign. And now these numbers are nice because they're right up along the axis here. All right. And when they're just up and down the axis, we can just swap that sign. But what if my number were something like we would say 4 plus J3 over it doesn't matter, over 2. Well, I don't just want to swap this sign. If this is what it looks like in the series, there's a plus sign in front of it, I don't want to just make this a negative sign. The conjugate of this number, and the notation for that is going to be 4 minus J3 over 2. You flip the sign on only the imaginary part.
Yep.
And we earlier 4 and 3s like that. So here's my angle 4, 3, 5. So this would be, if I wrote this as a polar, this would be e to the j 53, 30, 37, right? And if I wanted to conjugate that, then that would be 1/2 e to the minus j37. Because essentially, here's my complex number, here's my origin here. Then I come down the same magnitude or the same imaginary part, and I'm right here. So now we have, plus 37 degrees and then minus 37 degrees on this one. But as far as like a mathematical reason why odd signals, the coefficients of conjugates, man, the best I can give you is that odd signals are associated with sines and cosines, and even signals are associated with cosines. I haven't spent too much time on that, and I've never been asked that question. I mean, that's a good question. But that's the best I can give you, is that the sine is the odd signal, and if it's associated with that, then when you break apart and you do the complex arithmetic, then you're going to end up with conjugates. And any signal, when we talk about a square wave, I mean, that's when we model a square wave, we just have depending on how nice we want that square wave to look, depends on how many sinusoids we put into the square wave. But all a square wave is, how we get a digital square wave is we take a bunch of sinusoids with increasing harmonics, and we add them together. We have to scale them, meaning we might have to have some magnitude 1, magnitude 1/2, magnitude 1/4, magnitude 1/2 to the n. And then also we might want a negative. If we wanted a negative, well, could also be written as a phase shift of 180 degrees, right? So if I have a negative sine theta, which would look like sine starts from there, so that that would look like this. Well, that's also equal to sine theta plus 180 degrees. So that's just a phase shift, right? Because here's a normal theta, and when I shift it half a period, I'd be bringing it back, so that way it's back at the origin. But yeah, I mean, I don't really I feel like I'm just talking now, kind of going over the place. I'm sorry. Does that kind of help at least? Who was asking that question? Was it Carlos?
Yeah, no, it's good.
Okay. But yeah, so do we have I'm sorry, I ran my multi long. I didn't mean to take that much time. I'm running kind of low on time. Is there any and the midterm closes Monday night. I'll answer questions. I'm kind of busy tomorrow night, and then Sunday morning I got some stuff to do. But Sunday night and then all day Monday, I will be staring at the ed board waiting for questions, so that way I can provide any help I can. But tomorrow morning I'll be available, and then I mean, I always have my phone. I mean, if I can respond from my phone, I do. So, and I have those videos up, the midterm review videos. I go step by step. Like I make each problem take like 20 minutes, and it doesn't take 20 minutes. I go step by step, line by line through that, and I try to explain as much as possible. And then
That- I
Cameron,
like
what's that?
I like that method step by step, even though it's like kind of like people think, oh, you can't do step by. I like that method because it gives you allows you to see it visually and just understand it from like every little detail of it.
Yeah. I mean, it's if you guys take like 334 or whatever, I forget that's Dr. Ali, like his lecture videos are long as hell, but the thing is, like, they're awesome because he's constantly throwing in those little things like, hey, remember this, you know what I mean? Like just the simple stuff that you learned in an earlier course or an early math course that you forget. That's why I like doing stuff step by step, and I enjoy putting the videos together. So if you guys want more videos, and give me a problem, and I'll post the video. I'll make the video and post it. But
Yeah,
You said 334 circuits too.
Fantastic.
well, sorry, there was people talking there.
No, go ahead.
My bad, man. You said 334. You mean circuits too?
Yeah. Circuits too. Those
Too
are
late. I'm doing that now.
Oh
Too
yeah,
late.
those are good videos though, aren't they?
They're pretty good, Dr. Owasia. Yeah, he knows his stuff.
Oh, is it a new one? I had Dr.
Oh, you mean the lecture notes? That one guy, the Italian professor?
Well, that's 241. I thought. I don't know. I was well.
No, Doctor. Well, for the lab ones, we use Doctor. I'm taking it with Doctor Dillian Fan for circuits 2 online, and it's the Italian professor does all the lectures. It's the older professor for magnetics. And oh, you mean that one guy for circuits 2? I'm sorry. Yeah, you're right, Dr. Lee. My bad.
Yeah. The guy from circuits, the guy from 241 was pretty good too. He's more fun than anything.
Oh, he's funny. He goes, you mean the guy who goes, piece of cake? I'm like,
Yeah.
for you.
Yeah. For a
Jesus
goddamn
Christ.
genius like yourself, yeah. But
Maybe it's a piece of cake for you, but damn.
yeah.
It's only a 2-page proof. Piece of cake.
All right. If we don't have any more questions, fellas, then I'm gonna have to hop off here. Or ladies and gentlemen, if there's any ladies in here, I'm sorry. But
You've been great, man. And where link is it again? I'm trying to find the videos for the step-by-step problem because I look over them. I want to see the videos too.
if you look under the midterm review post on the ed board, there's a link that says video step-by-step solutions can be found at the playlist here. That word here has a link attached to it. And then also on one of the posts I did at the beginning of the year that says or the beginning of the term example problems worked out. That's a link to the actual my YouTube channel that has the midterm, the final, and then some random ones too. It has some convolution ones and everything like that. And I'm sorry, I saw the other day that there's ads on that. I don't make any money on that. I don't know how to get the ads off there. Apologize.
It's okay. It's all good, man.
Yeah.
Like and subscribe, support the channel, Patreon. It's all good, brother.
All right. Well, thank you. Thanks guys for coming. If y'all want to give me some feedback on my on how I went about this, then feel free to. I have thick skin. I've been in the Marine Corps for 16 years, so it ain't gonna hurt my feelings. So feel free to poke and jab at me.
Hoorah.
Good, man.
Rah.
We're on
Thanks
Semper
for your
Fi,
time,
man.
Mike.
Thank
All
you.
right. Yes,
Enjoy
sir.
your France, Mike.
Thank you.
Thank you.
Take it easy, fellas. But
You guys, Semper Fi, man. Take care.
never.